Alright, we're just going to go through integration now in this screencast and just get back to, we'll probably start from scratch because it's a long time since we looked at integration. We did touch on it last year, but now we're going to go through and complete the whole section. Also do some integrating or anti-differentiating of trig functions. Whole little section for us here, and it's the last really big section of the course. So if we go back, integration means anti-differentiation. Integration, or we can write here anti. Now, a reason I like anti-differentiation, and that's a bit of a mouthful, is it just does highlight that it's just the opposite operation to differentiation. So where we would take, we'd have the derivative of x squared is equal to 2x. We recognize therefore that the integral of 2x with respect to x dx equals x squared, but more than that, it's x squared plus a constant, because if we went back in here, what we need to understand is if I put a plus 1 in there, this stays the same, doesn't it? So how do I know when I integrate 2x here that I haven't got x squared plus something? Well, there's a good chance I've got the plus something there, and if the plus something, that can still be equal to 0, but we must allow for our constant. All right, so what did we do there? Well, we did this. If we're going to integrate x to the power of n with respect to x, then we're going to raise the power by 1 and then divide by that new power, plusing c on the end. All right, hopefully you remember that, but either way, it doesn't really matter. It's the opposite of differentiation. So we can get a whole bunch of practice at that, and it's pretty straightforward stuff. It gets a little bit more interesting down the track, but initially let's just have a look at, say, an example here. I'm just pulling one out pretty sort of at random. The integral of x plus the cube root of x. I can see here as an example. Right, then I would say that that's just equal to what we do with integration. We can split it. You see, we can just go, well, I'm going to integrate them separately. I'm not going to write cube root, I'm going to write x to the third. I should have stuck a little dx in there, please forgive me. So we integrate them separately. We don't need to write this out. I'm making the point that integrating, just like differentiation, you integrate each term separately. So integrating x gets us x squared on 2, and integrating x to the third gives us, right, add 1 to the power, that's 4/3. Dividing by 4/3 is, so I'll write it out, 4/3, and we divide by 4/3. I plus a c on the end. That needs obviously to be cleaned up a little bit. I'm going to times top and bottom by 3, so I end up with 3x to the 4/3 over 4 plus c, and that's my integral. Okay, looking for another example then. We have, I'll pause for a sec. So we might have an example here. All right, let's integrate 4 over x squared with respect to x. And again, I've got to rewrite this, haven't I, to 4x to the minus 2. And then I'm a chance I can raise the power by 1, so 4x to the minus 1, divide by that new power, and then just rewrite it a little more sensibly with a plus c on the end. And then for a bonus point, minus 4 over x plus c looks a little bit nicer. Okay, how about this this curly one here? Because if we look at 4 over x, we say, okay, that's got to be 4x to the minus 1, and then we say, right, well, let's now add 1 to the power and divide by it. Whoops, what's going on here? All right, we see a problem. But if we go back to our work on, here's one from the vault. What about the derivative of log x? Do you remember the derivative of log x? Well, I'll tell you, it's 1 on x. And even one step further, the derivative of log f of x, you remember, was f dash x over f of x. All right, just recall that stuff, because now we're going to use it with integration. If that's the case, then with integration, that would suggest, would it not, that 1 over x is equal to log base ex, or we can just write that as log x, sorry, ln x, and that should have a little dx in front of it, keep forgetting that. And if we've got more generally a fraction to integrate where the fraction is derivative over original with respect to c, then we are looking at that, the log of fx being our integral. So the log of the denominator. So let's have a look at this. We're not going to attack it in this way, are we? No. We're going to say forget that. 4x to the minus 1. I'm not even interested in that. What I'd like to do is look at this as, and this is something I can do. Did you know you could take that 4 out? So this is the same thing. You can remove constants, pull them out the front of the integral. So that with respect to x is 4. Now I've got derivative on function. So I've got 4 log x plus c as my derivative, and it even works quite nicely for, alright, have a look at this. If I go x squared, right, and down here I've got, right, I just changed it. I've got 3x squared over x cubed plus 1. So anytime you see a fraction now, when you're trying to integrate it, think, oh, especially if the power on top in the numerator is 1 less than the denominator's power, just check, is this actually the derivative of this? 3x squared, yes it is. And I can therefore use this result here, that my integral is just the log of the denominator, x cubed plus 1 plus c. Isn't that nice? One or two more examples. What about if we're trying to integrate something like, right, this big fraction here, 3x squared plus 2x plus 1 over x with respect to x. Right, now that is clearly the derivative of this is 1, so that doesn't work. I've got one term in the denominator. What we should do in this case is integrate each fraction separately. So we end up with 3x squared over x dx. Right, it's a bit painful to write it all out. 2x over x dx plus 1 over x dx. So this cancels down to the integral of 3x. This is the integral of 2. And this is the integral of 1 over x. And therefore we add 1 to the power, divide by it. 2 goes to 2x, and 1 over x goes to log x. And the plus c on the end. Just one more example. I'm going to show you another nice little result. If I've got a linear raised to a power, then the integral will be, right, we take that linear expression, we raise its power by 1, so far so good, divide by the new power, but multiply by the derivative of the bracketed term. This is very similar to that chain rule that we learnt with differentiation, if you remember. So for example, if we've got, let's find the integral of 3x plus 1 to the power of 4. Let's go with that. So this will go, right, just hold that intact, raise the power by 1, 5 by 3 underneath. So it's 3x plus 1 to the 5 over 15 plus c on the end there. Okay, I think that'll do. Got lots to get on with now. We can really get deep into chapter 9 over the next lesson or two. I'll see you soon.